Hello, so this is about Young's modulus, and it's a part of the AS Physics syllabus in topic 7. So, the Young modulus is basically just stress divided by strain, and it's an index actually, and it's used to get the stiffness of materials and not springs. So, you may have heard of Hooke's law. Hooke's law is basically K is F divided by X, and it gives us like the sort of stiffness index of a certain spring. However, the Young modulus gives us, it's very similar to Hooke's law, is that it gives us the stiffness of materials and not springs. So that's where the difference stems from. But other than that, they're pretty similar. So what is stress and strain? Well, strain, the definition is that it's the fractional increase in the original length of the wire. And so basically, when we do the same thing as we might have done before, and we have a setup where maybe we would have a certain wire and then we would have a load at this side, and this side would be kind of fixed. We would have this length, and then we might have an extension on top of that. So that's what it looks like. And the strain is basically the extension divided by the original length. And if this was X and before this was applied, this was L, then it would be X divided by L. And if you convert it to the same unit, so let's say we converted both of these into meters, then it is basically going to cancel out the meters because you can cancel it out. And that's why essentially strain is a ratio and it has no unit at all. So we don't need to worry about that. And it's just like a ratio that we put underneath. Stress, on the other hand, is defined as the force applied per unit cross-sectional area of the wire. And stress is force divided by cross-sectional area. So what that means is that if this had a weight, and we can denote that by W, that is basically the force. And we need to look at this wire. And if we look at it, and if we, make it so much bigger than it is, we would see that there is a cross-sectional area. And so basically, the cross-sectional area would be, weight divided by area that we see here. And that's what it is. So the unit for it is Newton per meter square, which is the same as the unit for pressure. So it can also be denoted as pascals, and both of them are acceptable. So why we need to take the lengths and the area into perspective is that to find out like the fundamental stretchiness or stiffness of a material altogether, we need to discard the shape of a certain object of that material and only think about the general material. So we need to take away the length and the cross-sectional area in order to get an accurate Young modulus. It's important to have a long and thin wire. And it's for two reasons. A long wire will stretch more, and a thin wire wouldn't stretch. A thin wire is important because a thick wire would not stretch as much for the same force. And in reality, X right here is extremely small and it's really, really hard to measure. So having a thick and short wire will mean that the extension is so small that it could not potentially be accurately measured in the laboratory. And therefore, that's the reason why if we want to take something like this in the laboratory, we need to make the extension as big as possible to reduce any errors in the experiment. So yeah, the definition for Young modulus finally is that it is an index for the stiffness of a certain material. And this is the graph that is plotted for the Young's modulus. And you can see that stress, which is force divided by cross-sectional area, is on the y-axis, and strain, which is extension divided by original length, is on the x-axis. And this is, again, just like Hooke's law, unconventional. Usually the manipulated variable, which is stress because we're manipulating the load that is added onto the wire, that should be on the x-axis, and that is so for all scientific experiments and data recording, but we decided to put it another way around, and that's because the gradient will basically give us Young's modulus. Remember that Young's modulus is stress divided by strain, and it's extremely convenient to just take a look at the gradient and say that that's Young's modulus, and that's the reason why it has been plotted in this way. Another way to kind of depict Young's modulus is by these symbols. So that's sigma divided by epsilon, and it's just sigma represents stress and epsilon is representative of strain. Unit, on the other hand, is also pascals or Newton per meter square. So you might remember that stress is basically pascals or Newton per meter square. Strain has no unit because it's just a ratio of extension to original length, and therefore we just take it as pascals or Newton per meter square. There's also a linear section and then a section where the wire that is under question will become plastically deformed or permanently deformed, and it will not obey Hooke's law anymore. So the Young's modulus and the gradient that we need to find must be in the part where the stress-strain ratio is constant or stress is proportional to strain, and that's when the material will obey Hooke's law, and that's when the gradient actually counts as the Young modulus. And that is about it.